Internet access is part of our branch connectivity scenario. DSL has become an effective option for corporate internet access using broadband technologies. Our implementation plan for the branch office scenario we're going to demonstrate includes the implementation of broadband technologies. Before we start our demonstration, let's briefly go through an overview of DSL. Remember, broadband technologies and connectivity are part of a broader objective of our branch upgrade scenario. We will start with our base topology shown in the figure, and then build internet connectivity with basic services such as NAT and DHCP as an alternative path into the headquarters router. We will then use this link as a backup to our private WAN using IPsec VPN tunnels. This will include some of the benefits and drawbacks, including the fact that it will not transfer routing protocol updates for traditional IGPs that are based on broadcast and multicast. For that reason, the third topic of our demonstration will be to run EIGRP across the IPsec VPN tunnel using GRE, or Generic Routing Encapsulation, protocol. As part of our migration path into decommissioning our private WAN link, we will test the forwarding of packets across both links using EIGRP's unequal cost load balancing. These objectives result in an implementation plan that will allow us to configure the branch and headquarters routers. Notice our first step in our implementation plan is to deploy broadband technologies. DSL is one of many broadband technologies that have become efficient and effective options for branch connectivity. Several years ago, it was identified that a typical voice conversation over a local loop only required the use of frequencies in the range of 300 Hz to 3 kHz. For years, the bandwidth over 3 kHz went unused. Advances in technology allowed DSL to use the additional bandwidth from 3 kHz up to 1 MHz to deliver high-speed data services over ordinary copper lines. For instance, asymmetric DSL, ADSL, uses a frequency range from approximately 20 kHz to 1 MHz. In order to deliver high bandwidth data rates to subscribers, a relatively small change to the existing telephone infrastructure was required. DSL is not a complete end-to-end solution, but rather a physical layer transmission technology similar to dial, cable, or wireless. DSL connections are deployed in the last mile of a local telephone network, the local loop. The connection is set up between a pair of modems on either end of a copper wire between the customer premises equipment, CPE, and the DSL access multiplexer, DSLAM, typically located at the central office, CO, of a service provider. Based on several physical layer distinctions, DSL presents several variants, some of which can be compared and contrasted using the table. When discussing the DSL variants, the following properties are worth comparing. The nature of DSL is the relation between downstream and upstream speeds. Synchronous DSL has, for example, the same speed in both directions, while asynchronous DSL has different downstream and upstream speeds. The maximum data rate is also another characteristic that we can compare. It defines the maximum speed that can be deployed with a certain type of DSL. You can see here speeds ranging from a few hundred kilobits per second up to 8+ megabits per second, up to the VDSL speeds which can achieve up to 52 megabits per second. The maximum distance is another limitation of certain types of DSL. It describes the maximum distance that a certain type of DSL connection can span from the CPE device to the DSLAM device across the local loop. In order to carry data services, DSL works in conjunction with other technologies. This results in several deployment modes. They all use a similar infrastructure, as shown here. The DSL Layer 1 connection from the CPE is terminated at the DSLAM. The data link layer protocol that is typically used over DSL is asynchronous transfer mode, ATM. A DSLAM is basically an ATM switch containing DSL interface cards. the DSLAM terminates the ADSL connections and then switches the traffic over an ATM network to an aggregation router. The aggregation router is a Layer 3 device where the IP connection from the subscriber terminates. IP packets over an ATM and DSL connection have to be encapsulated in some way. There are three approaches that exist. We are going to focus on PPPoA, or PPP over ATM. With this deployment option, a point-to-point protocol session is established between the CPE and the aggregation router. There is our PPP connection between the two devices. The CPE device must have a PPP username and password configured for authentication to the aggregation router that terminates the PPP session from the CPE. The aggregation router that authenticates the users can either use a local database on the aggregation router or a AAA server. After the PPP username and password have been authenticated, the negotiation takes place and the IP address is assigned to the CPE. After the IP address has been assigned, a host route is established both on the CPE and the aggregation router. The aggregation router must assign only one IP address to the CPE, and the CPE can be configured as a DHCP server and use NAT or Port Address Translation, PAT, to support multiple hosts connected via Ethernet behind the CPE. As we complete the configuration steps, we see all of the components of both the DSL architecture and of the basic IP branch services that hosts behind the CPE will require. ATM and dialer interfaces will establish the ATM virtual circuits and the PPP sessions. A dialer interface is nothing more than a virtual interface that is configured as an on-demand component. In other words, the interface will be up and active only after successful DSL subscriber authentication has taken place. Meanwhile, PAT, DHCP, and a static default route provide the IP addressing infrastructure to allow IP traffic to be carried over the DSL connection. A final configuration looks like this. Notice the ATM interface is a member of the dialer pool associated with the dialer interface. Again, the dialer interface is a virtual interface that will carry and have the IP address and Layer 3 information, but will use the ATM interface to access the DSL network. That's why you need to tie them together in the form of a dialer pool. Also, notice the ATM-specific configuration that establishes a permanent virtual circuit, PVC, according to information provided by the DSL service provider. The dialer interface initiates PPP connectivity, including services like user authentication. NAT is configured to translate traffic initiated at the LAN port into the IP address of the dialer interface, which can be obtained via DHCP from the DSL provider. You can see here the IPNAT-INSIDE command. LAN services are also provided by servicing DHCP requests on the LAN interface. The default route points to the dialer interface to initiate communication across the DSL connection. In verifying our DSL configuration, the best approach is to use the layered model to divide and conquer. At each layer, we will have components that help us understand the status of the connection, including DSL line status with the Show DSL Interface command, ATM PVC establishment with the Debug ATM Events command, PPP session negotiations, closer to Layer 3, for instance, debugging of PPP authentication, and the acquisition of an IP address, and finally, routing commands to verify connectivity. This list of verification commands is not exhaustive, but these commands will help display the components and verify and troubleshoot DSL connectivity. Looking again at our implementation plan, deploying broadband connectivity is an important component of our branch upgrade scenario. In this topic, we discussed and overviewed DSL as an example of such technologies. Now let's move on in our configuration and implementation plan in another topic.